So for question 1, we are asked to make a 150 milliliter solution of 0.035 molarity using substance A. To do this, we need to figure out the amount of moles so we can figure out the amount of grams we need to weigh out of substance A. You use the equation molarity equals moles over liter, and we know from the given numbers that we have 150 milliliters, which gives us 0.15 liters. Once we plug our information into the equation, 0.035 molarity equals X moles, in which we're trying to figure out, over 0.15 liters, we get 0.00525 moles. From there, we convert the moles using the conversion factors given for substance A, and we get 1.07 grams. To make this solution, you're going to weigh out 1.7 grams of substance A after you tar it out and make sure that your weight is at 0. You're going to use a spatula to weigh it out to 1.07. You're going to transfer this into the flask and then fill it up to the 150 milliliter line to finish your solution. So for question 2, we are asked to make a 250 milliliter solution of 0.05 molarity from the stock B solution that is 2.5 molarity. To do this, we use the equation molarity stock times the volume stock equals molarity of the final times the volume of the final. So stock final, after plugging everything in and then dividing the M stock onto the other side to get the volume final, you plug in your given numbers. So 0.05 molarity of the final solution and 250 milliliters volume of the final solution divided by 0.25 molarity of the stock solution, you're going to get your volume of the stock to be 5 milliliters. So to make the solution, you're going to use your 5 milliliter pipette and you're going to take it out of the 2.5 molarity substance B and transfer it into the flask, volumetric flask of 250 milliliters, because that is the amount of the solution that you're trying to get. And then with your diluted water, you're just going to fill it up to the 250 milliliter line, and that concludes your solution. For question 3, we are asked to titrate substance B into substance A and figure out the concentration of substance B. So to do this, we need to transfer substance B into the titration and substance A into the beaker. So we transfer 10 milliliters into the beaker using a pipette. And then the same, we transferred the 250 milliliter solution of 0.5 molar of what we believe it is into the titration. And then we titrated them with the initial of 12 milliliters to 20.55 milliliters. We titrated until we saw a color change. This came out to be 8.55 milliliters of substance A titrated into substance B titrated into substance A. So to figure out the concentration of substance B, we used the information we knew for substance A, the 10 milliliters to 0.010 liters, and then the concentration of substance A to figure out the amount of moles. From here, we use stoichiometry, and we know it's a 1-to-1 ratio is our assumption. And from there, it stays the same, and then we divide it by the amount of liters that we titrated it by. This is 8.55 milliliters that was of substance B titrated into substance A, which is 0.00855 liters. And after finding the answer to this to be 0.0409 molarity, that is our concentration of substance B. So for question number 4, we are trying to find the concentration of the unknown solution C. So to do this, we have unknown solution C, and we are going to transfer over with the pipette 20 milliliters into the beaker. So we have the new concentration of substance B that we found from question number 3. And we did another titration with substance C until we saw a color change. The initial volume came out to 10 milliliters and the final was 17.92. The difference between the two was 7.92 milliliters of substance B was titrated into substance C until there was a color change. To find the concentration of substance C, we are using the information we know from substance B. So from the 7.92 milliliters, which comes out to 0.00792 liters, and the concentration, the new concentration we know of the standardized substance B, we come to find 3.24 times 10 to the negative 4 moles of substance B. And because using stoichiometry that they have a 1-to-1 ratio, we have 3.24 times 10 to the negative 4 moles of 0.020 liters, because we have 20 milliliters transferred into liters of substance C, to find the concentration of substance C to be 0.0126 molarity. To figure out the concentration of the NaOH in the beaker, we need to use these equations right over here. Because we're trying to figure out the NaOH, but we are given the pH, we need to first figure out the pH by subtracting, or the pOH, by subtracting 14 minus the pH, which gives us 3.65. And after plugging in 3.65 of the pOH into this equation right here, we get the concentration after getting rid of the logs and raising it by 10. We get the concentration of NaOH ions, or the OH ions, to be 2.24 times 10 to the negative 4 molarity. And then now it wants to know how much the pH would be after it is diluted by 40 milliliters. So assuming that the volume is additive and we are adding the diluted water into the concentration we already have, we are going to use molarity of the initial times the volume of the initial equals molarity of the final times the volume of the final. So we plug in the information we already were given, 40 milliliters times the concentration of the NaOH, and we are trying to figure out the molarity of the final solution. So after adding 40 plus 40, we get 80 milliliters of the final solution after diluting the water. We get the molarity after dividing it and figuring it out. We get 1.12 times 10 to the negative 4. This is of the NaOH. AOH. And then after plugging in to find the pOH, because it is the OH, we get the pOH to be 3.95. And then subtracting it by 14, we get the pH of the diluted, after diluting the contents, to be 10.05. So for question 6, we are asked to find the concentration of the acetic acid in the buffer solution. We are given that Ka is 1.8 times 10 to the negative 5, and the buffer pH is 4.95. So to figure, and the concentration of the sodium acetate, the conjugate base, is 0.2 molarity. So we use the Henderson-Hasselbalch equation to figure this out, and we need the pKa. So we know the Ka, so to figure out the pKa, we just do negative log of the Ka, which comes out to be 4.74. So now we have everything to figure out the acid. So we plug in our givens, so our pH 4.95, and then our pKa is 4.74, plus log of the conjugate base, which we know is 0.2, and our acid is what we are trying to figure out. So after subtracting it by the pKa and putting it to the 10 to get rid of the log and dividing out, we get our acetic acid to be 0.123. So for question 5, you are trying to figure out how much would be left from a sample of 850 grams of radioactive material with a half-life of 5 hours after 24 hours and 48 hours. So to figure out, we're doing A first, 24 hours. You have to figure out K and use these two equations to figure out what would be left after. So to figure out K, you do ln over the half-life, which is ln over 5, knowing that the half-life is 5 hours. And you get 0.1386 to be your K. So then you get the equation your final versus your initial amount of your radioactive activity, e to the negative k, which is the k right here, times the time that you're trying to figure out. So it's 850. Our original amount is a e to the negative 0.1386 times 24 hours, which we are trying to figure out, and we get 30.53 grams. And then for B, we're trying to figure out 48 grams. You use the same equation, and we already know the K, so this time you just substitute instead of 24 hours, you're going to do 48 hours. And after plugging this into your calculator, you get 1.097 grams. So for question number 7, we are trying to figure out which takes more or requires more heat. Warming up 50 milliliters of substance A from 10 degrees Celsius to 60, or vaporizing 10 milliliters of substance A at its boiling point. So to do this, you require two different heat equations. For when you're just warming it up and you're not vaporizing, you use Q equals the mass times the specific heat times the change in temperature. So we have 50 milliliters and we need to convert it into grams to figure out the mass. Given that the conversion factor of the density, we convert the milliliters into grams, and then we just plug in all of the information. So the heat equals 39.6 grams after converting it to the specific heat, which after looking at the conversion is 2.5010 joules divided by grams times Celsius, and then the change in temperature is 60 minus 10, which is 50. After plugging this into your calculator, you get 4,969.8 joules, and you convert that into kilojoules, you get 4.97. When vaporizing 10.0 milliliters of substance A at its boiling point, you use a different equation, which is heat equals moles times the vaporization. We have to convert 10 milliliters into grams using the same density conversion factor, and you get 7.92 grams. So 7.92 grams converted into moles using the molar mass, you get 0.247 moles. And then plug everything into the equation. Q equals 0.247 moles times the heat of vaporization is 37.6 kilojoules per mole, and after multiplying it across, you get 9.29 kilojoules, which is more than the 4.97 kilojoules, so more heat is required when vaporizing. For the bonus problem, we are trying to figure out the individual H3O molecules in the 50 milliliter solution with a pH of 7 at 25 degrees Celsius equilibrium. So this equation comes out to be H2O plus H2O, which is water, is H3O plus O2. So we are trying to find out the H3O. So we know pH equals negative log and gives you that H3O concentration. So 7 equals negative log gives us the concentration. We come out, the concentration turns out to be 1 times 10 to the negative 7 molarity. And then we are trying to figure out the amount of moles in that molarity. So we know we have the milliliters, and we know molarity is moles over concentration. So to figure out the moles, you're going to multiply 0.050 liters, which is the 50 milliliters converted into liters, to get moles to be 5 times 10 to the negative 9. And then you're just going to multiply it by Avogadro's number to get the individual molecules of H3O in the solution.